Okay, Trig students, this is section 9.2. This will be the last section we cover. This will be the last section that I'm going to take grades on. And then the final. I know there's a couple others listed, but I'm not going to make you do those. I'm going to take them off. So this is it. So this is section 9.2. I'm going to try and see if I can get all of this in one recording. Okay, we're talking about vectors. I know 9.1 was our introduction into vectors, and it got kind of long and complicated. This is a lot more straightforward, I think. First, we're talking dot products. This kind of goes along with matrices, which we didn't really get to. You get a lot more into matrices when you get into like college algebra, but so dot products. If we are taking dot products, again, I recommend that you look through the PowerPoint that's in the class drive folder for this. But dot products, you're essentially multiplying the I components and then adding that to the product of the J components. So in this case, you're essentially multiplying your I's and then adding the product of your J's. So your dot product is going to be 1 times negative root 6 plus root 6 times 1. So this was your I's. This was your I component. These were your J components. So you take the product of your I's, okay, plus the product of your J's. When you find a dot product, it's not another vector. It's just a number. It's called a scalar. It is just a number. So this is going to give me negative root 6 plus positive root 6. Well, that's a big fat 0. Okay. And the angle between them, we have a formula actually that says cosine theta equals u dot v over, if you remember, we talked about this the last section, magnitude of u times the magnitude of v. So essentially, that means that theta is going to equal cosine inverse of u dot v over magnitude u magnitude v. Whoops. Okay, well, our u dot v is 0. So what's cosine inverse of 0? That is 90 degrees. So find the angle between them, 90 degrees. Okay, essentially when you have a dot product of 0, the two vectors are perpendicular or orthogonal. Orthogonal is just another fancier word for perpendicular. Okay, so find the angle between u and v to the nearest degree. That's your formula. Plug it in. Obviously your dot product was 0, so if you poke in your calculator, make sure your calculator's in degree mode, not radian, degree. Okay, then the inverse cosine of 0 is 90 degrees. Okay, hope that makes sense. Next page. Consider the following. Again, we're doing dot products. You are taking the product of the horizontal position plus the product of the vertical position. So we've got negative 3 times 1 plus 3 times negative 1. So negative 3 plus negative 3, this is going to give me a negative 6. Okay, hope that makes sense. Now, remember our cosine theta formula, so find the angle between u and v to the nearest degree. So cosine theta equals u dot v over magnitude u times magnitude v. Well, this is negative 6 over, now, let me do a little aside down here. Do you all remember that the magnitude of u is the square root of negative 3 squared plus positive 3 squared. Okay, so this is square root of 18, right? The magnitude of v, again, of course, those would be the dead spots in my board, square root of 1 squared plus negative 1 squared. Well, that's just square root 2. Okay, so now back up to our formula. This is root 18 times root 2, negative 6 over square root 36. It's negative 6 over 6, negative 1. So then that means theta is the inverse cosine of negative 1, which is 180 degrees. Okay, and the reason why, by the way, the reason why this up here is positive is because we're talking magnitudes, and magnitudes can only be positive. So 180 degrees is our angle. Hope that makes sense. Okay, just following the formula. Next one. Again, we're talking dot products, whether you name the vectors in terms of I and j, or whether you name the vectors and put them between the little brackets, it doesn't matter. You're still taking the product of the I position and adding that to the product of the j position. Okay, so we have 1 times 1 plus 1 times negative 1. So 1 plus a negative 1 gives me a big fat 0. Again, find the angle between. All that means is that we're taking the inverse cosine of 0, which is 90 degrees again. So remember, if you get a dot product of 0, that means the vectors are perpendicular, or typically when we talk lines or segments, we talk perpendicular. When we talk vectors, we call them orthogonal. It's the same thing. Okay. All right. Moving right along. Determine whether the given vectors are perpendicular. Now they're using the word perpendicular. It's the same thing. So again, you are taking the product of the horizontal positions plus the product of the vertical positions, and then seeing if you get 0 or not. So 6 times negative 2 plus 4 times 3, negative 12 plus 12 is 0. So that's a big fat yes. Okay. Down here, again, we're taking the product of the horizontal position plus the product of the vertical position. So 0 times 6 plus negative 4 times 0. 0 plus 0 is, of course, 0, so that's still a yes. Okay. Next one. Find the indicated quantity assuming that, and they give us the vectors u, v, and w. Now, you can do the dot product that way, or wait a minute, stop. I think I skipped one. I forgot to scroll down. I had another one. Okay, sorry. Now, keep in mind on u on this one, my u is actually 4i plus 0j. Okay, so when I go to do my products, I'm doing the i's and the j's. Okay, so it's 4 times negative 1 plus 0 times 6. So negative 4 plus 0 is negative 4. Is that perpendicular? No. Sorry, I thought it was odd that I had skipped one. Okay, now this page. So you can either do it u dot v plus u dot w, or we actually have some properties, and again, they're in that PowerPoint. If you want to look, there's a little table on them. This actually also equals, if I kind of factor out the u, if you will, it equals v plus W. So it's like I'm factoring out the U, and now that's a dot, okay? Sometimes I kind of say multiply. When we're talking vectors and multiplication, it's dot products. So it's the same thing. We just have to remember if we're talking vectors, we're not talking about a single number times another number. We're talking about a dot product. So you can kind of, again, factor out the U, if you will, and add the V and W together first. So that's probably what I'm going to do. So I'm going to rename, well, let me first of all add my V and W together here. So I plus 3i gives me 4i, and negative 3j plus 2j gives me negative 1j. Okay, so now my U is 6i plus j. So now I'm doing dot products, product of that plus product of that. Okay, so I've got 6 times 4 plus 1 times negative 1. So 24 minus 1 is 23. Okay, that would be my answer. And down here, they already kind of did it for us. So again, let's combine my i's and j's. Here I'm adding them. Okay, I'm not doing dot products here, but I and 3i, so this is v plus w, gives me 4i once again. Negative 3j plus 7j gives me positive 4j. And again, I'm just going to recopy my u. So now if I do dot products here, the product of the I components plus the product of the j components. So I've got 5 times 4 plus 1 times 4, 20 plus 4, obviously would give me an answer of 24. Okay, hope that makes sense. All right, I don't think I had anything under that. No. All right, next page. Find the work done by the force F in moving an object from P to Q. Now, again, in your PowerPoint, highly recommend it. There is a formula that says work equals force times distance. Now, when we're talking vectors, again, that's a dot product. Okay, force dot product distance. So distance, here's the deal for distance. Distance, we're literally looking at the change in our x position and the change in my y position. That's going to give us the distance vector. Okay, so my distance is going to equal, I'm going to do them instead of i's and j's, I'm going to do them in those brackets. So it's going to be 3 minus 0, that's the change in my horizontal position, comma, 6 minus 0 is the change in my vertical position. So my d vector is 3 comma 6. Okay, my f vector, so this is d, my f vector, I'm just going to rewrite as 2 comma negative 4. Okay, so then my work, again, dot product, it's the dot product of 2 negative 4 and 3 6. So again, dot products, product of your first position plus product of the second position. So 2 times 3 plus negative 4 times 6. So 6 plus negative 24 equals negative 18. Okay, work equals force times distance. Okay, and again, when I say times, when we're talking vectors, that's a dot product. That's how we multiply vectors. Okay, this one says find the work done by the force in moving an object from P to Q. Same kind of deal. Okay, first of all, this right here, we're going to find the distance. Distance is going to be 200 minus a negative 1, comma, 1 minus 1. Y'all see that? Again, change in your x position, comma, change in your y position. Horizontal movement, comma, vertical movement. So that gives us 201, comma, 0. That is my distance vector. Okay, my force vector, of course, I'm just going to rewrite it, is 300, comma, 60. Again, whether you use brackets, whether you use IJ, it really doesn't matter. So your work, again, is the dot product of 300, comma, 60 times 201, comma, 0. Well, again, product of the first position plus product of the second. Now, the product of the second position is not going to matter because 60 times 0 is 0. Okay, but what I really have to do is take 300 times 201, and that gives me the magic answer of 60,300. Now, again, I didn't write the second part. Maybe I should. That's 60 times 0. Okay, which is obviously 0. So 60,300, that's the work done. Okay. All right, next page. The force F, which equals 4I minus 9J, moves an object 2 feet along the x-axis in the positive direction. Okay, what that means. 2 feet along the x-axis in the positive direction means that the distance is 2I. That's the horizontal movement. There is no J. Okay, so that means if we do it in bracket form, that is 2, comma, 0. That's my vector for distance. So find the work done if the unit of force is the pound. So force, they already gave us. So work equals force, which is 4, negative 9, times, or dot product, 2, comma, 0. So this is 4 times 2 plus negative 9 times 0, which is just 8 foot-pounds of force. Okay. I hope that makes sense. All right, let's look at this lawnmower one. A lawnmower is pushed a distance of 250 feet along a horizontal path. Okay. Right off the bat, 250 feet along a horizontal path. That means that my distance is the vector 250, comma, 0, just like the one above it. Okay, if we're going horizontally 250 feet, that means that the horizontal vector is 250 and there's no vertical change. So my vector is just 250, comma, 0. Okay, sorry. By a constant force of 50 pounds, but the handle of the lawnmower is held at an angle of 30 degrees from the horizontal. Now, if you remember back in section 9.1, in order to find the I and J components of a vector, the I component was the magnitude or force times cosine of the angle, and the J component was the magnitude or force times sine of the angle. Okay, so the force we're talking about, let me use a different color. So our force, we've got 50 pounds. Okay, again, it's 50 pounds of force, but we're at an angle. So we've got to find the I and J components of that. It's not just an even, Steven, 50. It's 50 times cosine 30 degrees. That gives me my I component. Okay. And then we've got 50 times sine 30 degrees. That gives me my J component. Again, I hope that rings a bell from section 9.1. Okay. If it doesn't, go back and take a look. So this is going to give us, if you poke that in your handy dandy calculator, again, I'm going to put it back in brackets. This is going to get us 25 root 3, comma, 25. Okay, 25 root 3i and 25j. Okay, so now, again, work equals force times distance. So work equals, here's my force vector dot product, that's times. My distance vector is that. So, again, 25 root 3 times 250 plus 25 times big fat 0. So 25 root 3 times 250 is approximately 10825.32. And I believe it said something about round your answer to the nearest whole number. So 10825. Okay. Foot-pounds. All right. I hope that made sense. Okay, next. We are cruising right along. Now, these, I'm a total geek, but I kind of like them. Same kind of deal, okay? A car drives 600 feet on a road that is inclined 12 degrees to the horizontal. Okay, right off the bat, that vector, okay? That vector is going to be 600 times cosine 12 for your I component and 600 times sine 12 for your J component. So that is going to be force. Actually, let me go ahead and put it in brackets. So 600 cosine 12 degrees, that's your I component. And again, your J component is 600 sine 12 degrees. Okay, now that, if I poke that in a handy dandy calculator, oh, sorry, I called that force. That is actually your distance, because that's like how far the car traveled. I apologize, I labeled it incorrectly. So that is going to give you, handy dandy calculator time, 586.89, comma, 124.75. So that's your distance vector, okay? Your force vector, okay, is like 0, 2500, okay? Now, I don't really know how to say it. Doesn't really matter that the 2500 is negative because we're talking about forces. So really doesn't matter in this problem that it's a negative 2500. So just keep that in mind. So your work, okay, again, is force times distance. So 0, 2500 times, or dot product, 586.89, comma, 124.75. And again, dot product, we're taking the product of the I component plus product of the J component. Obviously, the first one is going to give us a big fat 0. So I'm really just concerned with the J component. So 2500 times 124.75 gives us approximately 311,867.54. Okay, which, if we read the directions, round your answer to the nearest 1,000 foot-pound. So the nearest 1,000. So that is 312,000. Okay. Hope that makes sense. All right, last two, and then we're done. Woohoo! Okay. Now, on this one, we are talking about different forces. If you look in your PowerPoint, they talk about W being a combination of U and V. And anyway, it's the last several pages of your PowerPoint. I'm going to try to summarize here. So let's just look at this one first. A car is on a driveway that is inclined 20 degrees to the horizontal. If the car weighs 2,755 pounds, find the force required to keep it from rolling down the driveway. Okay, so here's what we got. That's like horizontal ground level, okay? Here's our driveway. This is 20 degrees. Here's my sad little car. I'm just making it a box. No wheels or anything, because I'm a loser and can't draw. Okay, now we're talking about our W being the combination of a U and a V vector. So we've got this, let me use some different colors here. This is what we would call the U vector. Perpendicular to that is what, dude, I can't even do that straight. It's what we would call the V vector. And then the W is the weight. That's our gravity. Okay, so here I have straight down, perpendicular to the horizontal ground. Okay, here's this perpendicular. The blue up here, U and V are perpendicular to each other. But my W here, that's my weight of the car. That's 2,755, and that's a J vector, okay, because it's vertical, right? So that's J. Again, you can mark it negative, but it really doesn't matter for the problem, so I just leave it. Now, vector U, actually, let me write this. Vector U is the force that tends to roll the car down the driveway. Okay, just so. Force that tends to roll the car down the driveway. Okay, vector V, okay, is the force experienced by the surface of the driveway. Okay, so U is the force that tends to roll the car down the driveway. D is the force experienced by the surface of the driveway. Now, the magnitude of U, okay? The magnitude of U is the component of W along U, which, actually, that's what we're looking for here, okay? It says, if the car weighs 2,755 pounds, find the force required to keep it from rolling down the driveway. That's the magnitude of U, okay? So it's the component of W along U, which equals, okay, 2,755, that's the weight of the car, times cosine of, now, here's where it gets interesting. Okay, think about this triangle right here. Okay, if this is 20 degrees, this right here is my U. Okay, well, what degree measure is U? Well, if that's a right triangle, that's a sad little block here, but if this is a right triangle, this is 20 degrees, then that makes U, the angle U, 70 degrees. Okay, that's what goes over here. 2,755 times cosine 70 degrees. Okay, that's the magnitude or force of U. Okay, so all we have to do is plug that in our handy dandy calculator. Okay, and we get approximately 942.27, but then what did they say? Round your answer to the nearest pound. So 942. That would be my answer. Okay. So again, please, please, please look in your PowerPoint, and it talks about the connection, actually W equals U plus V. Okay, that's kind of the, and then they talk about one being the component of the other and the component of U along V, or anyway, look in your PowerPoint. It does a lot better explaining with pictures. Tried to write out what I could here on this one. Okay, last one. A package that weighs 400 pounds is placed on an inclined plane. If a force of 40 pounds is just sufficient to keep the package from sliding. Now, let me back up. It's kind of like what we did up here, only now we're solving for the theta, okay? On this previous one that we just solved about the car, the force of 942 pounds is what's keeping that car from rolling back down, okay? So that's what they're talking about in the one below it here. It takes a force of 40 pounds to keep the package from sliding back down the incline. Okay, so then we have to find the angle of the inclination. So we're kind of going in reverse of what we just did on this one above. Okay, so hang with me. Again, let me try to draw a sad picture. So here is horizontal. Okay, here is my inclined plane. We are trying to find theta. Okay, here is my sad little package. All right, and the package weighs 400 pounds. So this perpendicular to the horizontal ground, that is my weight, which is 400. That's my like J component. And of course, that's also a dead spot in my board. It's Murphy's Law. Okay, now, remember from up above here, this is like my U, okay? Perpendicular to U is the V. Okay, we haven't really talked about V. That this assignment kind of stops at U, so lucky you guys. But that's my U and my V. So W, as you see up above, is made up of U plus V. U is like your horizontal component. V is like the vertical component. Okay, so U here, they told us what U is. U, magnitude of U is 40. Okay, that's magnitude or force, whatever you want to call it. So magnitude of U is 40. Now we know from the one up above, right, that also means that 40, that magnitude of U equals 400. That's the weight. Actually, let me write it in red because that's what I wrote my weight in. It's 400 cosine theta. Nope, actually, let me back up. It's not theta. I don't want to name it the wrong thing. This, if you remember, just like up above, if I redraw that triangle, okay, this is my theta. I'm going to call this my U. Okay, U degrees, if you will. All right, so this is 40 That's my magnitude or force of u. That's the force that's required to keep it from sliding down the incline, equals 400 times cosine of u. Okay, well, u is what we're trying to solve for, right? So this means 40 over 400 equals cosine u. Well, that's 1/10. So that means that u is the inverse cosine of 1/10. Again, 1/10 comes from 40 over 400. So that equals, if I poke that in my handy dandy calculator, approximately, I should have had my squiggles here, 84.26. Now, that's u, that's not theta. But how do we find theta? Okay, well, we know from our little right triangle, my sad little right triangle picture, right, that theta equals 90 minus u. So 90 minus 84.26 is 5.74. And then what did the directions say? Round your answer to one decimal place. So this would be approximately 5.7. Okay? And that's it. 5.7 degrees is the incline. Not a very big incline. But then again, for a 400-pound package, we only needed 1/10 of that force to keep it from sliding down. So obviously, you can see that the bigger the incline, the more force is required to keep it from sliding down. Okay? This, we had just 1/10 of the weight of the package as a force to keep it from sliding. So just by thinking of that logically, if you only have 1/10 of the force to keep it from sliding down, the incline must not be very great. Okay? All right, guys, this completes, hallelujah, praise the Lord, section 9.2. Last new section that I'm going to make you do for Trig. And the reason I'm stopping here is this is the last section that he has any questions on for the final. He has some more assignments out of chapter 13, but I'm going to take them off. So I didn't figure that would hurt anyone's feelings. Anyway, yay. If you guys have any questions, holler at me. Okay? Have a good one.